Okay, so let's derive another equation here. For this situation, we assume we have an object starting at rest. Therefore, it has zero kinetic energy. So whatever work is applied to that object will be the change of kinetic energy that it experiences will be its final kinetic energy. So this kind of summarizes what I just said. Here we're, instead of force times distance, we're just putting in a different variable, just delta x. But still the distance, well, technically displacement. And so that work we add to the object equals the change in kinetic energy. And since we start from zero kinetic energy, that also equals the actual final kinetic energy. But we want to come up with an equation for the kinetic energy in terms of variables that it currently has, not variables that indicate what has been done to this object in the past. Because we may look at a speeding bullet and we might not know what force was applied to it, or how long it's traveled with that force being applied to it. Or a car, we might just want to be able to measure its mass and velocity, but we don't know exactly how much force went into accelerating it for how long. So let's, instead of using F and delta x, let's use Newton's second law, force equals mass times acceleration, and insert ma instead of F. And then from the kinematic equations, we can use another equation for delta x. And since we would like to be able to describe something's kinetic energy in terms of its current velocity, let's use one of the equations with velocity as a variable in it. And what we're going to have to do is solve this equation for delta x, so we have a definition to insert for delta x here. So this step was actually two steps. I subtracted v initial squared from both sides, and then I divided both sides by 2a to isolate delta x. And now we can put this in place of delta x in this equation. And we might not know its acceleration, so we probably don't want to have acceleration in our final equation, but we kind of get a hunch that it might cancel out because we get an acceleration down here and an acceleration up here. So we can kind of see that if we have an acceleration in the expression for both f and x, that hopefully they'll just cancel out, and they do. Like we have a divided by a, and that ends up that we don't have a in our final equation, which is great. We actually have now an equation in terms of only the mass of an object, its final velocity, and we decided at the beginning that this object starts at rest, so the initial velocity is just going to be 0. So we don't even need to write that. We can just say Vf and leave out the minus V0 because it is 0. And the A canceled out on the bottom. So that leaves us with a simplified expression for kinetic energy in terms of just the mass of something and its current velocity, which are things we can measure. And we can rewrite this. M times Vf squared over 2 is the same as half mv squared.